The interview landscape has undergone a dramatic transformation. The modern system design interview represents a significant paradigm shift, moving away from algorithmic puzzles toward comprehensive architectural exploration. Unlike coding rounds, which typically have deterministic answers, these sessions utilize open-ended problems to simulate real-world engineering challenges. The core objective is to evaluate how a candidate navigates ambiguity. Interviewers look for senior-level signals by assessing the ability to justify decisions through rigorous trade-offs. This involves balancing consistency against availability or latency against throughput. It is important to understand that the goal is not to find a single perfect solution, but rather to demonstrate a systematic approach to scaling. True mastery in this context involves articulating exactly why specific strategies are appropriate for modern system constraints. When approaching the system design interview landscape, it is essential to distinguish between product-focused and infrastructure-focused rounds. In a product-centric interview, the core components are API design and data modeling. The primary objective is building features, making the relationship between entities and the way the front end consumes data paramount. Conversely, infrastructure rounds require a deep dive into storage engines and throughput. Here, the focus shifts to how the system handles massive loads, consistency models, and network bottlenecks. Success in these interviews requires tailoring your depth of technical detail. Avoid over-engineering the database internals of a simple application, but ensure you do not ignore disk I/O when building a distributed file system. Always match your technical expertise to the specific requirements of the role. Functional requirements define specific system behaviors. It is essential to clarify the what before exploring the how. The process begins by identifying core features, determining the essential actions the system must perform to provide value. For example, an email client must be capable of sending and receiving messages. Second, we must determine user personas. Understanding who interacts with the system, whether it is an end user, an administrator, or an external API, shapes the required functionality. Finally, we establish system boundaries. By explicitly defining what the system will and will not do, we prevent scope creep. This ensures the engineering team remains focused strictly on the intended domain logic and essential outputs. Non-functional requirements define the operational constraints of a system, focusing on how well it performs rather than its specific behaviors. In the delivery framework, we prioritize three critical pillars. First, scalability and availability ensure the system can handle growth and remain operational during failures. Second, latency and durability address responsiveness and data persistence. A system must be fast and must never lose committed data. Finally, security and compliance protect against threats and meet legal standards. This checklist ensures architectural integrity. Without these elements, even a functional system will fail in production. It is necessary to quantify these metrics early to guide infrastructure choices and trade-offs effectively and reliably. Capacity estimation, often referred to as back-of-the-envelope calculation, is a vital discipline for designing scalable systems. We begin by identifying the number of daily active users, or DAU. For instance, if a system serves 100 million users and each user performs 10 actions daily, the system must handle 1 billion requests per day. To determine the requests per second, or RPS, we divide 1 billion by 86,400 seconds, which results in approximately 12,000 RPS. It is important to note that peak load typically doubles this average, reaching 24,000 RPS. Next, we calculate storage requirements. If we process 1 billion posts daily, with each post averaging 100 kilobytes, the system requires 100 terabytes of storage per day. Projecting this over 5 years, the total storage capacity needed would be 180 petabytes. Bandwidth requirements are derived by multiplying the RPS by the average request size. In this scenario, 12,000 requests per second multiplied by 100 kilobytes results in a bandwidth requirement of 1.2 gigabytes per second. Finally, memory needs are often estimated using the 80-20 rule. By caching 20% of the daily data, we can ensure low latency and efficient resource allocation. This level of analytical rigor is essential to prevent system failure and ensure robust performance at scale. Selecting the appropriate transport protocol is a critical decision for system performance. While HTTP 1.1 is ubiquitous, it often suffers from head-of-line blocking because it processes requests sequentially. HTTP 2 addresses this limitation through multiplexing, which allows multiple concurrent streams over a single TCP connection using binary framing. This approach significantly reduces latency. For internal microservices, gRPC is often the superior choice. It leverages the benefits of HTTP 2 but replaces JSON with protocol buffers, or protobuf. Protobuf provides efficient binary serialization and strict typing, which reduces both payload size and CPU overhead. In practice, HTTP 1.1 or HTTP 2 should be used for public-facing REST APIs to ensure broad compatibility. However, gRPC is preferred for high-throughput, low-latency internal service-to-service communication. This strategy effectively balances interoperability with raw performance. WebSockets enable full duplex, bidirectional communication over a single TCP connection, beginning with an HTTP handshake. This process eliminates header overhead, delivering the low-latency updates essential for applications like gaming. When the requirement is strictly for server-to-client updates, server-sent events, or SSE offer a unidirectional stream over standard HTTP. SSE is inherently simpler and supports automatic reconnection natively, while WebSockets are designed to handle complex two-way traffic. Both protocols maintain persistent connections to eliminate the lag associated with traditional polling. It is important to note that WebSockets require more server resources and specific browser support. Generally, WebSockets are ideal for interactive applications like chat, while SSE is better suited for scenarios like LiveScore updates. Together, these technologies revolutionize modern web interaction by maintaining an open communication pipe that is efficient, reliable, and effective. Load balancing occurs at different layers of the OSI model. Layer 4 operates at the transport level, routing traffic based on IP addresses and TCP or UDP ports. It is extremely fast because it does not inspect the application data, making it ideal for high-performance needs. Conversely, Layer 7 is application-aware. It inspects HTTP headers, cookies, and URL paths to make routing decisions. This allows for sophisticated logic like AAB testing or microservice routing. Layer 7 also handles SSL and TLS termination at the edge, decrypting traffic before it reaches backend servers. This offloads intensive cryptographic processing and simplifies certificate management across the entire distributed infrastructure. When deciding between REST and GraphQL, the choice depends on how you intend to manage data interaction. REST treats data as resources identified by specific URLs. This simplicity, however, often results in overfetching, retrieving unnecessary data, or underfetching, which necessitates multiple requests to complete a single view. GraphQL solves these challenges with a query-based model, enabling the retrieval of specific fields in a single round trip. A key consideration is caching. REST utilizes standard HTTP caching because each resource has a unique URL. Conversely, GraphQL typically uses a single endpoint via POST requests, making native browser caching difficult to achieve. Choosing between them requires balancing REST's predictable caching and simplicity against GraphQL's precise data fetching and reduced network overhead. This decision should be guided by the specific needs of your system architecture. API reliability hinges on effectively managing resource consumption. Pagination is a critical technique used to prevent massive payloads. While offset-based pagination is intuitive, it often suffers from performance degradation as offsets increase and is vulnerable to data shifts. Cursor-based pagination solves these issues by using a pointer to the last record, ensuring constant time lookups and data consistency. To prevent service overload, rate limiting must be implemented. The token bucket algorithm allows for occasional bursts while maintaining a controlled average rate. Conversely, the leaky bucket algorithm enforces a steady, fixed processing speed. Finally, DDoS protection strategies, including edge filtering and traffic scrubbing, safeguard against intentional volumetric attacks. These mechanisms are essential for ensuring robust availability, security, and long-term system-wide operational stability. Relational databases prioritize ACID properties: atomicity, consistency, isolation, and durability, ensuring strict data integrity for structured tabular data. These systems rely on predefined schemas and vertical scaling. Conversely, NoSQL models embrace the BASE philosophy: basically available, soft state, and eventual consistency, favoring availability over immediate consistency. NoSQL handles unstructured or complex data, such as documents or graphs, while offering schema flexibility. While SQL scales vertically by adding hardware power, NoSQL scales horizontally by partitioning data across multiple commodity nodes. Choosing between them depends on the data shape. Use SQL for complex joins, and use NoSQL for high velocity, massive scale, or evolving data structures. This choice defines both performance and reliability. Storage models dictate how data maps to memory, which explains the shift away from traditional relational tables in specific use cases. Key value stores, such as Redis, treat data as opaque blobs indexed by unique keys. By residing in memory, they achieve sub-millisecond latency, making them an ideal choice for caching. Conversely, document stores like MongoDB are designed to handle semi-structured hierarchical data. They store rich objects, allowing for complex queries on internal fields without the constraints of rigid schemas. While relational databases prioritize ACI seed compliance, these NoSQL models often embrace eventual consistency to ensure high availability within distributed systems. Choosing between these models depends on whether the architectural priority is lightning-fast lookups or the flexibility of managing nested data structures within a single record. Relational models often struggle with massive scale and complex relationships. Wide column stores, such as Cassandra, optimize for high write throughput by utilizing log-structured merge trees, or LSM trees, and partitioning data across clusters. These systems can handle petabytes of data by organizing it into flexible rows with many columns, which is ideal for time series data or logging. Conversely, graph databases like Neo4j prioritize relationships. Instead of relying on expensive joins, they use index-free adjacency, treating connections as first-class citizens. This makes traversing complex social graphs or recommendation engines highly efficient. Choosing between these models depends on your query patterns. Use wide column stores for high-volume writes and graph stores when the value lies in the deep interconnectedness of data points. The performance variation between database read and write operations is primarily driven by the underlying indexing structures. B-trees, a standard in SQL databases, organize data into sorted blocks to enable highly efficient searching, which is ideal for read-heavy workloads. However, this organized structure necessitates complex rebalancing during every update, introducing overhead for write operations. In contrast, log-structured merge trees, or LSM trees, are designed for high-speed writes. They treat incoming data as simple appends to memory, which are later flushed to disk. While this makes LSM trees exceptionally powerful for write-intensive applications, read operations may become slower as they often need to scan through multiple layers of data. Ultimately, every indexing strategy involves trade-offs. They all require additional storage and consistent background maintenance to maintain system performance, reliability, and high scalability. The cache-aside pattern is a fundamental strategy for effective data management. During a read operation, the application first queries the cache. If a cache hit occurs, the data is returned immediately. In the event of a cache miss, the application fetches the required data from the database, stores it in the cache, and then returns it to the requester. This approach implements lazy loading, which significantly reduces the overall load on the database. For write operations, the application updates the database first and then invalidates the corresponding cache entry. This process ensures that subsequent read requests fetch the most current data. A key advantage of this pattern is system resilience. If the cache becomes unavailable, the system remains functional by falling back to the database. By balancing performance with data consistency, the cache-aside pattern has become the most common integration strategy in modern distributed systems. Maintaining consistency between the cache and the database is a critical requirement in distributed systems. Consider the write-through strategy. It updates both the cache and the database simultaneously. This ensures immediate consistency. However, it is often avoided because every write operation must wait for the database, which increases latency significantly. While safe, it is inherently slow. Conversely, the write-back strategy updates only the cache initially and synchronizes with the database at a later interval. This offers superior performance and high write throughput. However, it introduces a major risk. If the cache fails before the synchronization occurs, the data is lost forever. Architects must weigh these trade-offs carefully, deciding whether to prioritize the reliability of write-true or the speed of write-back. This choice ultimately defines the resilience of the system. Understanding these trade-offs is essential for effective data management. The CAP theorem states that a distributed system can only provide 2 out of 3 guarantees: consistency, availability, and partition tolerance. Consistency ensures that all nodes see the same data simultaneously. Availability guarantees that every request receives a response. Partition tolerance allows the system to continue functioning despite network failures. In a distributed network, partitions are inevitable, forcing a strategic choice between consistency and availability. CP systems prioritize data integrity, potentially rejecting requests during failures to ensure correctness. AP systems prioritize uptime, accepting writes that might lead to temporary data divergence. Understanding these trade-offs is crucial for designing resilient architectures tailored to specific business requirements and failure modes. The CAP theorem describes system behavior specifically during network partitions. However, to understand how a system performs during normal operation, we look to PACLC. PACLC extends the CAP theorem by posing a 2-part question. If there is a partition, does the system choose availability or consistency? Else, in the absence of a partition, does it choose latency or consistency? This else clause is critical. Even without network failures, replicating data across multiple nodes introduces inherent latency. If you require strong consistency, the system must wait for all replicas to acknowledge a write, which increases latency. If you prioritize low latency, you risk serving stale reads. Modern databases, such as DynamoDB and Cassandra, are classified by how they manage these fundamental trade-offs during both failure and steady-state operations. This extension provides architects with the necessary clarity for making informed design decisions. Scaling data involves two primary strategies: vertical and horizontal scaling. Vertical scaling, often referred to as scaling up, involves upgrading a single server's hardware by adding more RAM or faster CPUs. While this approach is straightforward, it eventually hits a physical ceiling where hardware becomes prohibitively expensive or simply unavailable. In contrast, horizontal scaling, or scaling out, involves adding more machines to the cluster. This strategy offers theoretically infinite growth, but introduces distributed complexity, requiring effective data partitioning and load balancing. From an economic perspective, vertical scaling is more cost-effective initially, but scales poorly over time. Horizontal scaling utilizes commodity hardware, which reduces costs at scale, although maintenance complexity increases significantly as the node count grows. Ultimately, this fundamental choice between scaling up or scaling out defines the core architecture of a system. Sharding horizontally partitions data across multiple nodes to scale beyond the capacity of a single machine. Range-based sharding assigns data based on value intervals, such as alphabetical names. While this approach is intuitive, it risks uneven distribution if data clusters within specific ranges. In contrast, hash-based sharding applies a hash function to the shard key, distributing data uniformly across nodes. However, this method complicates range queries. Selecting an effective shard key is critical, as a poor choice leads to hot shards, where a single node is overwhelmed by disproportionate traffic. To mitigate this, access patterns must be analyzed to ensure the shard key provides high cardinality and maintains a balanced load across the entire cluster. In distributed systems, scaling data efficiently is a critical requirement. Traditional hashing techniques, such as key modulo n, cause massive data movement whenever nodes are added or removed. Consistent hashing solves this problem by mapping both keys and nodes onto a logical circular space known as the ring. Each key is assigned to the first node encountered when moving clockwise around this ring. When a node is added or removed, only a small fraction of keys, roughly 1 over n, require relocation. This contrasts sharply with traditional methods, where nearly all keys must be moved. To ensure balanced data distribution and avoid hotspots, we utilize virtual nodes. By mapping multiple points on the ring to a single physical server, we can achieve a more uniform distribution and significantly minimize resharding overhead. Consistent hashing maps keys and nodes to a circular identifier space. However, basic consistent hashing often suffers from non-uniform data distribution, creating hotspots. To mitigate this, we introduce virtual nodes. Instead of a physical server occupying one position, it maps to multiple points on the ring. This granularity ensures a balanced load. Furthermore, virtual nodes handle heterogeneous capacities. We assign more virtual nodes to powerful servers. When a node fails, its keys redistribute across various neighbors rather than one successor, enhancing reliability. However, managing many virtual nodes increases metadata overhead, requiring a careful balance between system complexity and distribution accuracy. In distributed systems, achieving agreement among nodes is fundamental, and we accomplish this through the use of quorums. In a cluster consisting of n nodes, we define specific counts for read operations, denoted as R, and write operations, denoted as W. The condition where R plus W is greater than n is critical. This mathematical requirement guarantees that at least one node in any read set will contain the most recent write, thereby ensuring data consistency across the system. To manage these operations effectively, we rely on consensus protocols such as Paxos and Raft. Raft, in particular, utilizes a leader election mechanism to maintain order within the cluster. Should the leader node experience a crash, the cluster is designed to automatically elect a new coordinator. This high availability for coordinators is essential as it prevents system-wide failures, ensuring that the distributed state remains synchronized and reliable throughout the entire cluster. Scalability in modern system design often hinges on the strategic separation of read and write concerns. One common approach is the implementation of read replicas. This involves duplicating the primary database to offload heavy read traffic, which allows the primary instance to focus exclusively on write operations. While effective, this pattern introduces the challenge of replication lag, where replicas may momentarily fall behind the primary database in terms of data synchronization. For more complex architectural requirements, Command Query Responsibility Segregation, or CQRS, takes this separation a step further. CQRS utilizes entirely different data models for updates and queries. Commands are responsible for handling state changes, while queries are dedicated to fetching data. This decoupling significantly optimizes both performance and scalability. However, it is important to note that this approach increases overall architectural complexity. Balancing these patterns is essential for supporting massive user bases while maintaining system responsiveness and ensuring data consistency effectively and reliably. Scalability fundamentally hinges on decoupling. Message queues facilitate this through the producer-consumer model, where producers append tasks to a buffer, allowing consumers to process them asynchronously. This architecture absorbs traffic spikes, preventing system collapse by buffering requests during peak loads. However, delivery guarantees are critical. At least once delivery ensures no data loss but requires idempotent consumers to handle duplicates. Exactly. Once delivery is ideal but complex, often requiring distributed transactions or unique identifiers. By offloading heavy tasks from the synchronous request-response cycle, we ensure durability and horizontal scalability. This allows for the independent scaling of producers and consumers based on demand, ensuring the system operates effectively and reliably. In distributed systems, failures are inevitable. When a service call fails, the standard response is to implement retries. However, naive retries can inadvertently overwhelm a struggling system. To mitigate this, we implement exponential backoff with jitter, which adds randomized delays to prevent the thundering herd effect. If failures persist, the circuit breaker pattern is triggered. This pattern transitions from a closed to an open state, providing a critical fail-fast mechanism. By stopping requests immediately, it prevents cascading failures and allows the failing service the necessary time to recover. During this recovery period, we ensure graceful degradation by returning cached data or default values. These patterns transform fragile connections into resilient, robust architectures, maintaining system stability even when individual component failures occur. In distributed systems, network failures frequently necessitate retries. When a client fails to receive an acknowledgement, it typically rescinds the request. However, without idempotency, this can lead to unintended consequences, such as a payment being processed multiple times. We solve this by using idempotency keys, which are unique identifiers sent by the client. The server stores these keys and the resulting state. If a duplicate key arrives, the server returns the cached response instead of re-executing the logic. This ensures that f of x equals f of fx, making operations safe to repeat. This pattern is critical for financial transactions and order processing, where consistency is non-negotiable despite unreliable network conditions. It guarantees system reliability and data integrity. When managing simultaneous data updates, two primary strategies are employed: pessimistic and optimistic locking. Pessimistic locking operates on the assumption that data conflicts are likely. To prevent these, it immediately locks the relevant row or table, locking other transactions until the current operation is complete. While this method guarantees strict data consistency, it can significantly limit system throughput. Conversely, optimistic locking assumes that conflicts are rare. Rather than using locks, it relies on version-based checks. Before committing a save, the system verifies that the data version has not changed since it was last read. If the version has changed, the update fails, necessitating a retry. Optimistic locking is the preferred choice for high concurrency environments where the frequency of conflicts is low. However, pessimistic locking is essential when the cost of a conflict is too high or when updates are frequently clashing. Coordinating operations across multiple servers requires a robust distributed locking mechanism. One common approach is the red lock algorithm used by Redis, where a client must successfully acquire locks from a majority of nodes. However, reliance on synchronized clocks can be problematic, as clock drift can compromise the safety of red lock. To address this, fencing tokens are employed. These are unique, monotonically increasing identifiers. If a process is delayed, for instance, by a garbage collection pause and its lock expires, the target resource will reject any request carrying an outdated token. Zookeeper provides an alternative approach using ephemeral nodes, which ensures that a lock is automatically released if the client disconnects. It is important to recognize that network partitions and process pauses are inevitable in distributed systems. Without fencing tokens, distributed locks remain fragile. Therefore, always validate these tokens at the storage layer to maintain system integrity. Content delivery networks, or CDNs, utilize points of presence referred to as POPs at edge locations to minimize latency. In a pull model, a CDN fetches content from the origin only upon a user request, which is known as a cache miss. This approach is ideal for high-traffic sites. Conversely, the push model requires the origin to proactively send updates to the CDN, making it suitable for static, infrequent changes. Managing time to live, or TTL, is crucial, as it defines data freshness. However, when urgent updates occur, manual cache invalidation at the edge is necessary to purge stale data. Balancing these models ensures the efficient delivery of both static and dynamic assets globally across distributed networks. Object storage solutions, such as Amazon Web Services S3 or Google Cloud Storage, are engineered to manage massive volumes of unstructured blobs with high efficiency. Unlike traditional file systems, object storage employs a flat hierarchy and unique identifiers. A critical optimization within this framework is the implementation of presigned URLs. Instead of routing heavy binary data through an application server which would exhaust valuable bandwidth and CPU cycles, the server generates a temporary cryptographically signed URL. This mechanism provides the client with direct, time-limited access to the storage bucket for performing uploads or downloads. By decoupling these processes, the backend remains lightweight, managing only metadata and authorization. Meanwhile, the specialized storage infrastructure handles high-throughput data transfers securely and at a global scale. Geospatial indexing is the primary solution for efficiently solving the find nearby problem. Standard B trees are insufficient for two-dimensional queries because they are designed for one-dimensional data. Geohashing addresses this by interleaving the bits of latitude and longitude to generate a base 32 string. This process effectively maps a two-dimensional area onto a one-dimensional line, where longer prefixes represent closer proximity between locations. Alternatively, quad trees offer a hierarchical approach to spatial partitioning. In this structure, each node recursively splits into 4 quadrants until a specific capacity limit is reached. This allows for highly granular searches in dense urban environments while maintaining a sparse structure in rural areas. By utilizing these specialized indexing structures, companies like Uber can scale proximity searches effectively, reducing the search space from millions of individual points to just a few localized buckets. Real-time processing manages continuous data flows through the implementation of stream processing. Apache Kafka utilizes immutable event logs, where data is appended and organized into partitions to ensure high scalability. This architectural design allows multiple consumers to read data concurrently. Apache Flink excels at stateful stream processing by maintaining internal state for complex computations. To effectively manage infinite data streams, we employ windowing techniques to group events by time or count. This enables the performance of aggregations, such as sums or averages, providing low-latency insights. Unlike traditional batch processing, streaming treats data as an unbounded sequence. This approach requires robust state management to handle out-of-order events and system failures, ensuring exactly once semantics for reliable, real-time analytical results. Modern distributed systems require these capabilities for effective data handling. In distributed systems, traditional ACIC transactions often fail due to network latency and service isolation. The Saga pattern solves this by breaking a long-lived transaction into a sequence of local transactions. Each service updates its own database and triggers the next step in the process. If a step fails, the system executes compensating transactions, undoing previous successful actions to restore balance. We implement this via choreography, where services react to events, or orchestration using a central controller. This shifts our focus from immediate to eventual consistency, ensuring system reliability without the performance bottlenecks of two-phase commit protocols. This approach manages complex workflows effectively across microservices. In distributed systems, security hinges on the critical distinction between authentication and authorization. Authentication is the process of verifying identity, whereas authorization focuses on granting specific permissions. The OAuth 2.0 framework provides the standard for delegated access, often utilizing JSON Web Tokens, commonly referred to as JWTs. These tokens are stateless, carrying claims directly within their payload, which eliminates the need for resource-intensive server-side session lookups. However, this statelessness introduces significant revocation challenges. Once a token is issued, it remains valid until its expiration, unless a centralized blacklist is actively maintained. For access control, there is a notable transition from role-based access control, or RBAC, which assigns permissions to static roles, to attribute-based access control, or ABAC. ABAC evaluates complex policies based on user, resource, and environmental attributes, providing the finer granularity necessary for robust system protection. Designing a service like ByteLaw requires a reliable mapping from long URLs to unique short aliases. A critical decision in this design is the method of ID generation. While auto-incrementing integers are simple to implement, they present a single point of failure and can reveal sensitive data such as the total count of links. In contrast, distributed Snowflake IDs offer high scalability and guaranteed uniqueness without the need for constant coordination. Once a 64-bit ID is generated, we utilize base 62 encoding. This alphanumeric approach transforms the ID into a compact string, such as 6JK9A. For high-performance redirection, HOT, URLs are cached in Redis to minimize database overhead. Finally, to ensure the system remains performant, user engagement is tracked via asynchronous analytics events, allowing for detailed data collection without impacting the speed of the redirect process. Bit.ly handles millions of redirections per second, necessitating a read-heavy optimization strategy. Since reads outnumber writes by orders of magnitude, the system employs aggressive caching using Redis or Memcached to store popular mappings. To minimize latency globally, geographic load balancing directs users to the nearest edge server. As the link count reaches billions, a single database becomes insufficient. To scale, database partitioning or sharding is implemented, using the hash of the short Uniform Resource Locator or URL to distribute data across multiple nodes. This ensures horizontal scalability and high availability, allowing the system to resolve redirects efficiently without bottlenecks. This robust architecture guarantees performance at a massive scale. To deliver social media feeds efficiently, we utilize two primary fan-out strategies. The first is fan-out on write, often referred to as the push model. This strategy pre-computes feeds by pushing new posts into every follower's cache immediately upon publication. While this ensures lightning-fast read operations, it faces significant challenges with hotkeys issues when high-profile accounts or celebrities post to millions of followers simultaneously. The second strategy is fan-out on read, known as the poll model. This approach aggregates posts only when a user explicitly requests their feed. While this method saves storage space, it inherently increases read latency. Modern, large-scale systems like Twitter employ a hybrid approach. They push posts from regular users to maintain speed, while pulling content from celebrities to manage load. This hybrid model effectively balances write loads and read performance, ensuring a seamless user experience across massive, globally distributed, and highly scalable social networks. Efficient news feeds require optimized storage and sophisticated ranking. Timeline metadata is stored in distributed NoSQL databases like Cassandra, mapping user IDs to post IDs for fast retrieval. The ranking logic balances recency, showing the latest updates, with relevance, utilizing machine learning models to predict engagement based on user affinity and content quality. To minimize latency, cache warming strategies are implemented, pre-calculating feeds for active users and storing them in in-memory stores like Redis. This ensures that when a user logs in, their personalized timeline is instantly available, significantly reducing database load and improving the overall user experience during peak traffic periods effectively. To protect distributed clusters, we must choose between local and centralized enforcement. Local rate limiting is fast, but fails to maintain a global quota across multiple nodes. Centralized enforcement using Redis effectively provides consistency. For precise sliding windows, we utilize Redis sorted sets. Each request adds a timestamped member. We prune expired entries using zrem range by score and count remaining ones with zcard. To minimize latency in the critical path, we execute these operations via Lua scripts, ensuring atomicity and reducing network round trips. This architecture robustly balances strict limit enforcement with the high performance required for modern, scalable, distributed microservices. Dropbox achieves its high-speed synchronization through the strategic use of chunking. While fixed-size chunks are straightforward to implement, they are inherently brittle. A single insertion can shift the entire file, effectively breaking deduplication. To address this, variable-size chunking utilizes Rabin fingerprinting to identify content-based boundaries, maintaining consistency even when edits occur. These chunks are stored within content-addressable storage and are indexed using their SHA-256 hashes. By implementing client-side hashing, the system avoids re-uploading data that the server already possesses, significantly reducing bandwidth consumption. Server-side hashing is then employed to validate these uploads. This architecture transforms large files into a collection of unique, reusable blocks, ensuring that only new data is transmitted across the network. This approach maximizes efficiency and storage utilization throughout the global infrastructure. Dropbox ensures file consistency across devices by utilizing a decoupled architecture. When a file is modified, the client updates the metadata database, which is responsible for tracking file versions and chunk hashes. To notify other devices of these changes, the system employs long polling. Unlike standard polling, the server holds the request open until a change occurs, which significantly reduces latency and network overhead. In scenarios where multiple devices edit the same file simultaneously, Dropbox uses versioning to manage potential conflicts. The system detects these conflicts by comparing the parent version ID. If a mismatch is identified, both versions are saved, allowing for manual resolution by the user. This robust synchronization loop ensures a seamless experience across diverse platforms and varying network conditions, maintaining both efficiency and reliability. Designing a platform like YouTube requires the capability to handle massive upload volumes for a wide variety of devices. To manage this complexity, a directed acyclic graph, or DAG-based pipeline, is utilized to execute tasks such as transcoding, thumbnail generation, and watermarking concurrently. Transcoding is the process of converting raw video into multiple resolutions and formats to ensure compatibility. To maintain smooth playback under varying network conditions, adaptive bitrate streaming is implemented using protocols like HLS or Dash. This enables the client to switch quality levels dynamically based on available bandwidth. Furthermore, storage efficiency is critical at this scale. A storage tiering strategy is employed where hot videos, those that are highly popular, are kept in high-performance SSDs or CDNs. Conversely, cold videos, which are rarely accessed, are moved to more cost-effective, high-capacity storage. This approach effectively balances system performance with infrastructure costs. Processing billions of ad clicks requires a robust infrastructure. We utilize log-structured storage, such as Kafka, to ingest events sequentially, ensuring high throughput and durability. To make sense of this data, we define aggregation windows, fixed time intervals, like 1 minute to sum the clicks. However, network delays often cause late arriving data. We handle this using watermarks, which track progress and event time rather than processing time. This allows the system to wait for stragglers before finalizing results. By decoupling ingestion from processing, we achieve real-time analytics at a massive scale, maintaining accuracy despite the chaotic nature of distributed event streams. This architecture ensures long-term reliability. Observability transcends basic monitoring by explaining why systems fail. It is built upon 3 essential pillars: metrics, logs, and tracing. Metrics provide aggregated numerical data to track performance trends, while logs offer granular, time-stamped event records for detailed debugging. In a microservices environment, distributed tracing is critical. It utilizes span IDs to track requests across service boundaries, allowing us to reveal hidden bottlenecks. Effective observability requires alerting on service-level objectives, or SLOs, and service-level indicators, or SLIs, rather than raw metrics like CPU usage. This ensures the focus remains on user-impacting issues. By correlating these signals, we gain deep insights into production health, enabling rapid incident response and system hardening to achieve high operational reliability. Reliability in distributed systems is not a matter of chance. It is a deliberate engineering outcome. Chaos engineering, a discipline pioneered by Netflix with their Chaos Monkey tool, represents a fundamental shift from reactive troubleshooting to proactive experimentation. By intentionally injecting faults, such as terminating server instances or inducing network latency, engineers can verify whether auto-healing mechanisms function correctly under duress. A critical component of this practice is the strict control of the blast radius. This ensures that experiments are contained and do not lead to catastrophic production outages. This methodology is invaluable for uncovering hidden dependencies and complex race conditions that standard unit testing often fails to detect. Ultimately, the goal is to build confidence in a system's resilience by demonstrating its ability to withstand turbulent conditions. If a system cannot survive a control failure, it cannot be expected to survive the unpredictable nature of a real-world production environment. This proactive approach is essential for maintaining high availability systems. Average latency often obscures the reality of system performance. In distributed systems, the focus must shift to tail latency, specifically the P99 and P99.9 percentiles. This is critical because the unlucky 1% of users often experience the most significant performance degradation. In microservice architectures, tail latency is amplified. Consider a scenario where a single request triggers calls to 100 different services. If each service has a 1% chance of being slow, the probability of the overall request being delayed increases dramatically. To mitigate this, we employ a strategy known as hedged requests. This involves sending the same request to multiple replicas after a brief delay. The system accepts the first successful response, effectively bypassing any outliers. This approach ensures consistent performance, even when individual components encounter background noise or garbage collection pauses. Cloud economics demands architectural precision. A critical factor in budget management is understanding why data transfers can be so costly. Egress costs are incurred whenever data leaves a provider's network. Therefore, prioritizing data locality is essential to minimize these fees. When managing compute resources, the challenge lies in balancing availability with price. Spot instances offer substantial discounts for workloads that can handle interruptions, whereas on-demand instances provide the necessary stability at a premium price point. Furthermore, the choice between serverless and provisioned infrastructure depends heavily on the workload profile. Serverless architectures can scale to 0, making them ideal for bursty traffic patterns. Conversely, provisioned infrastructure remains more cost-effective for steady-state, high-utilization systems. Architects must treat cost as a first-class constraint, optimizing every byte and cycle to ensure financial efficiency without compromising performance. This balance defines the essence of modern cloud engineering. Before finalizing any architecture, a rigorous design review is mandatory. First, identify any single points of failure, or SPOF. If the failure of one node halts the entire system, redundancy is missing. Next, evaluate back pressure and flow control mechanisms. It is essential to determine if the system can signal upstream producers to slow down during traffic spikes, or if it will simply crash under the load. Finally, verify security at every layer. A defense-in-depth strategy ensures that a breach in one component does not compromise the entire environment. This checklist transforms a theoretical model into a resilient, production-ready system. Always validate these critical pillars to ensure long-term robustness, reliability, and overall scalability. System design interviews evaluate more than technical knowledge. They assess how you navigate ambiguity. You must drive the conversation, transforming a vague prompt into a concrete architecture. Do not wait for permission. Lead the requirements gathering and component selection. Proactively identify bottlenecks, such as single points of failure or latency spikes, before the interviewer points them out. This demonstrates foresight. Crucially, listen for interviewer hints. If they nudge you toward a specific area, pivot immediately. They are your collaborators, not adversaries. Effective navigation involves balancing broad abstractions with deep dives, ensuring the design remains cohesive while addressing critical scaling challenges.